Hello guys, welcome to today's session. In today's session, we are going to start with most commonly used logarithms. Okay, 95% of the times when we are asked to solve any logarithm problem, we are asked to solve it with base 10, okay, or okay. So these two logarithms are very commonly used. Okay, it doesn't mean that we don't use the other logarithms with other bases. We do use that, but these are these are most commonly used. Okay, so the most commonly used logarithms are common logarithm, okay, common logarithm, and natural logarithm. Okay, so common logarithm, what does it mean? Common logarithm means that base 10. Okay, so common logarithm refers to base 10. Okay, and natural logarithm refers to base e. Okay, now what is this e? Okay, what is this e? uh, when we did a session on exponential functions, there we had a separate session on very specific exponential function e raised to the exponent x that is derived from the calculus. Okay, and we in that session we had constructed the number e known as the Euler's number, and the value of e, it is approximately around 2.71828 and so on. Okay, so we had a separate session on this uh, number e, okay, base e, Euler's number, and you can go to the exponential the videos on exponential functions. There you can find this separate lecture on this, and this is a very important number if you want to find out how things grow naturally, or if you want to understand the power of compounding. Okay, compounding in context of your money, you have to go through this number, or you have to go through the concept of e. Okay, now there are a few things about this number which I want to highlight here, is that this number, okay, this number does not have a finite decimal value. Okay, it doesn't have finite decimal value. Okay, and it is irrational constant, means that you cannot represent it in the form of p by q. It is an irrational number. Okay, so because you cannot represent it in the form of p by q, it does not have a finite decimal value, means that this thing after decimal, it is not finite, it just goes on and on and on and on. And the thing that we have written here, it is just the approximate value. Okay, it's just the approximation we have used. Okay, it does not have a finite decimal value. Okay, I hope this thing is clear to you, and you can also visit that session to know more about e. Okay, now common logarithms are the logarithms with base 10, and natural logarithms are the logarithms with base e. So how to represent these common logarithms? I can represent it like log of x to the base 10, right? And natural logarithms, log of x to the base e. Now, natural logarithms are also represented as L and X. Okay, so this means natural logarithm. Okay, so whenever you see L and X, it means natural logarithm. Okay, so natural logarithms are also represented by ln, and sometimes you see that you sometimes what happens is that you don't see any base with logarithm. Okay, so whenever you don't see any base with logarithm, you have to assume that it is base 10. Okay, so when base is not defined or not given, sorry, not given in the question, then it is understandable that you have to assume it 10. Okay, then few more things about common logarithm is that it is also known as Brigian logarithm. Okay, and this one is also known as Napierian logarithm. They are just named after the mathematician who have contributed a lot about these specific types of logarithm. Okay, so I hope it made sense to you. Okay, now there is one more thing here, that is the relationship. Now, a relationship between your your natural logarithm and common logarithm, or your common logarithm and your natural logarithm. So the relationship is that log of x to the base e, it is equal to 2.303 log of x to the base 10. Okay, this is very important, especially especially when you deal with logarithm in chemistry. Okay, when you have to find out the pH, okay, then you see that you have to use this conversion formula, but you have to understand that how this has been derived, right? So just have a look. Is it visible? Oh yeah, it is. Now see here, what uh, I can do here is, okay, now this thing, log of x to the base e, okay, this thing, please tell me if you agree with me, this thing can be written as log of x to the base 10 divided by log of e to the base 10, right? Now how did I write this thing? I just have used base changing theorem, okay, which says that, what is the base changing theorem? It says that log of m to the base n is equal to log of m to the base a by log of n to the base a. So I just made use of this thing here, and I hope you agree with it. Okay, now this thing is log of x to the base 10 by, this thing is log of 2.71828, so on, to the base 10. Now you have to take log of this value with respect to base 10, and if you do so, then this value, it's going to be 1 over point 0.4342, and here log of 10, sorry, log of x to the base 10. Okay, so if you take the log of this uh, Euler's number with respect to base 10, so this thing is going to be 0.4342. Okay, and when you divide this thing by 1, it's going to be 2.303 log of x to the base 10. So you must understand how and why did we write here log of x to the base e is equal to log of x to the base 10. Okay, so log of x to the base e is equal to 2.303 log of x to the base 10. So these are few things that you have to remember, you have to understand. Okay, and this conversion, it is very important. You will find its rule in some other fields too, like in physics, in chemistry. Okay, then this E, it is very, very important. I recommend you to go through that separate session that we did on E, Euler's number. Okay, how did we derive this number, and then how did we plot the graph? Still remember that the slope is equal to the height of function. This is a very special function, okay, and um, it is derived, it is constructed from calculus. Okay, so these are few of the things that you have to understand. Okay, now we will go ahead with next important topic, and the next important topic is characteristics and Mantissa. Okay, next important topic that we are going to learn is characteristics and Mantissa. Okay, so I'm going to write the name. Next topic is characteristics and Mantissa of log. This is the next topic. This is the next topic. Now, see here. First, we have to remind us few things. Okay. First thing, that whenever we do logarithm, we have to remind ourselves, or we have to tell ourselves that logarithm is only defined for positive numbers, right? Means that you cannot find the logarithm of any negative number. Okay, I hope this made sense, because this is the definition of logarithm. Okay, so logarithm, it is only defined for positive numbers, right? Now, whenever we find the logarithm of any number, any positive number, what happens is that we get some value in return, or I can say that we get some value as the answer. Okay, so here, for example, what I'm trying to say is that if I am taking the logarithm of any number with any base, then here I am going to get something as my answer. Let's say that my answer here is n, right? Because I am taking here, what's the condition? It is that x must be greater than 0 and a must be greater than 0 and a should not be equal to 1. Okay, so whenever we take logarithm of any number, so what happens is that we get some value in return. Now, thing here is that the value that we get in return, means this n, this value, it is the combination of this value, it is the combination of inti it is a combination of integer and fraction. Okay, so whenever we take log of, again I'm repeating it, whenever we take the log of any positive real number, the value that we get, or the value that it returns, it contains, or it is the combination of integer and fraction. Okay, so for example, what I'm saying here is that log of 2 to the base 10. Okay, if we do log of 2 to the base 10, the value is 0.3010, right? The value is 0.3010. So I'm saying that this value that we get here is the value that we get here has integral part and fractional part. Fractional part, right? So the integral part is known as characteristic, and the fractional part is known as mantissa. Okay, so whenever you find the value of any log, so then the integral part of that value is known as the characteristic, and the fractional part of that value is known as mantissa. Okay, so let's do one example here. You will have more clarity. Okay, you will have more clarity. So what I am doing here is that okay, what I will do here is that what I will do is I will just take log of 20 to the base 10, right? Now, log of 20 to the base 10, it is equal to 1.3010, because see here, not every time you have to use your scientific calculators or the log tables. There are what you can do is that you can learn or you can memorize the the values of few numbers. Understand? Like it's better if you memorize the value of log 2, log 3, log 10, log 20. See here, if you know the value of log 2, then it's very easy to memorize the value of log 20, log 200. Okay, so you have to find those patterns, and better if you memorize few values. Okay, so this is the value that I get here for log 20 to the base 10 is 1.3010. Now if I break this value, okay, if I break this value, what will I get? So I have, see here, I have something after the decimal and I have something before the decimal, right? So I can write this thing as, I can break it down to 1 plus 0.3010, right? So this is the integral part. So this is going to be my characteristic, and this is the fractional part. So this thing, the fractional part is going to be mantissa. Okay, so characteristic means the integral part, and mantissa means the fractional part. Okay, now we can take one more example for better clarity, right? So if I take log of here, log of 30 to the base 10. Now log of 3 to the base 10, it is 0.4771, right? So log of 30 to the base 10, it is 1.4771. Right now, if you look at, you can find, okay, you can find the value of this log using the table or using your calculator. So it has to be this. Okay, so if you break it down, it's going to be 1 plus 0.4771. Now see here, this is your integral part. So integral part means here characteristic, and this is your fractional part. Fractional means Mantissa, right? Fractional means Mantissa. Okay, now uh, here I want to discuss because this is not the end of this story. There is something more to it. Okay, and what is that? Here, please note one thing here is that very important, very important. Okay, so here characteristic, and here Mantissa. Okay, now the characteristic of a log. Now see here, this part is the characteristic of log, right? So characteristic, it can be positive, it can be 0, and it can be negative. Okay, so the characteristic of a log can be positive, can be 0, can be negative. Okay, I will show you how it can be negative. Okay, but the Mantissa, it must always be positive. Okay, so the Mantissa of a log, it must always be the positive. Okay, now let's take an example. Let's take an example. Let's take an example of log 1 by 200 to the base 10, right? Let's take an example of log of 1 over 200 to the base 10. Okay, now what happened is that this thing can be written as log of, right? Uh, can I write this thing as log of 200 minus 1, right, to the base 10, right? And this thing can further be written as minus of log 200 to the base 10. I did nothing. Log of x to the power n is n log x, so minus comes in the front, and then this thing can be written as minus log base 10, and it can be 2 multiply by 100, right? So can I use here log product rule? Log m multiply by log of m multiply by n, which is equal to minus log base 10, here log 2 to the base 10 minus log of 100 to the base 10, which is equal to, this is minus log 2 to the base 10, and here this can be written as 10 square, so it will be minus 2, right? Minus 2. Why? Because this is the exponent rule. Okay, log of x to the base n is n log x. So, and here log of 10 to the base 10. So uh, we know the value of log 2, the value of log 2 is 0.3010. Sorry, the value of, what's the value of log 2? The value of log 2 is 0.3010, and here we have minus 2, so it's going to be minus 2.3010. Okay, so this is going to be your log, this is going to be your log of 1 by 200 to the base 10. This is minus 2.3010. Now see here, this is very, very important. What we have said here is that the characteristic, it can be positive, 0, and negative. So now let's break this number. So can I write this number as minus 2, right? And minus 0.3010, right? So here the characteristic, it can be positive, 0, and negative. So we are fine with minus 2 because that's what the definition of characteristic says. But the mantissa must always be positive. But here, if you see, we are just getting the negative value of mantissa. So according to the definition, this should not be valid, right? So we have to make mantissa positive, and to make this mantissa positive, what I will do here is that I will just add and subtract 1. Okay, so here minus 0.30. What I did here, I just add and subtract 1 to make this value positive. Okay, so this minus 1 will go with minus 2, so it's going to be minus 2 minus 1, it's going to be minus 3, and 1 minus, see here, 1 minus 0.3010, so it's going to be 996. Okay, so it's going to be plus 0.6990. Okay, so what's going to be the characteristic? Characteristic is going to be minus 3. This is your characteristic CH. And mantissa, it's going to be 0.6990. This is the mantissa, because mantissa has to be positive. I hope it makes sense. All right, so we can take one more example here. Okay, we can take one more example here. We can take one more example, log of 1 by 300 to the base 10. Okay, so this thing can be written as log 300 minus 1 to the base 10, and it can be written as log of 300 to the base 10, which is equal to, so it's going to be minus 2.4771. Okay, because I know the value of log 3, it is 0.4771, so I can easily figure out the value of 30, log 30, log 300, log 3000. Okay, so this is the value of log 1 by 300 to the base 10. Now see here, if I break down this value, it's going to be minus 2, and here minus 0.4771. Okay, so if this is going to be my characteristic, it is fine. Why? Because my characteristic, sorry, not my characteristic, but characteristic of a log, it can be positive, it can be zero, it can be negative. So this is, since this is negative, so we should not have any problem, because according to the definition, this is valid. But here, the Mantissa of log is negative, and by definition, it must always be the positive. So what I will do here to, so what I need to do here, I have to make this guy positive, right? So here, what I can do is, to how I can make it positive, minus 1 plus 1, right? And here minus 0.4771, right? So if I simplify it further, so it's going to be, we have to subtract 0.4771, so 9 here, 10 here, 9, 2, 2, and here 5, right? So it's going to be plus 0.5229. Now see here, this is your characteristic, and this guy, positive guy, is your Mantissa. Okay, I hope this concept of characteristic and Mantissa is clear to you. Now here, the thing is that this characteristic and Mantissa, yes, I forgot one thing here. Okay, see here, for example, uh, this is the value. Okay, so what happened is that this is the value, uh, minus 2 plus, this is the value, minus two, sorry, minus 3 plus, sorry, minus 3 plus 0.5229, right? So what we do is, when we write, or when we combine both of, them, we write it like this. We put bar on 3. This horizontal bar on 3 means negative 3, and here we put decimal, and here we just write. Okay, so this means characteristic, and horizontal bar on the characteristic means that, it means that the integral part is negative, right? So just put this thing in your mind. Now see here, you now this thing, characteristics and Mantissa, they exist for all logs, means that it doesn't matter what base are you using, if you are using base e, or if you are using base 10, if you are using base 5, you are using base 2, it has nothing to do with the base. Okay, means that this thing of characteristic and Mantissa, it is, or it is valid for all logs. Okay, so you can even find characteristic and Mantissa of logs with base e, or with base 2, with base 5. Okay, so that's all about it. Very important. Now we are going to study few of its uses. Okay, so where and how can we use, how and where we can use it. Okay, so uses. Okay, uses. So now see here, because we are studying mathematics, so better if we talk about its application in other forms of math, right? So now see here, it has its uses or application in arithmetic, right? Arithmetic, it's the primary branch of mathematics where we study numbers, right? All integers, fractions. So that's what arithmetic is all about. Okay, basic operations: addition, subtraction, division, multiplication, right? So uh, this thing of log has its application in arithmetic. Okay, and the uh, first use or first application, I would say, first application is about the first application is about finding the number of digits. Okay, so see here. So the first application that we are going to speak here is about finding the number of digits. So finding the number of digits means that how many digits are going to be there in any number. Now, for example, here, if I write a number and I will say that how many digits are there, so you will reply, oh, this is a very easy question and the number of digits here are 3. If I ask you how many digits are there in this number, you will say it's very easy, 4. But what if I say that, okay, how many digits are going to be there in this number? Now, you have to find out the value of this, right? And then you have to calculate. So now, see here, as the power is going to increase, the number is going to be big. So it's going to be a very tedious task to find out the number of digits in the given number. Okay, so now the beauty of logarithm is that using logarithm we can easily find out how many digits are going to be there in any number. Okay, so let's start with it. Okay, let's start with it. Okay, now first what I will do is that I will take few numbers here first. For example, here I will take number 100, and here I will take number 1000, and here I will take number 10,000. Right? So what happened is that now see here, this application, this application, uh, so this is the application of logarithm, right? But logarithm with only base 10. Okay, using common logarithm. Okay, using common logarithm. Okay, so the applications that we are going to do, it means that uh, the application holds true only when we use common logarithm. Okay, so if what now see here, what I will do is that if we take the log of these numbers, common log, right? Here, log of 10, and here, log of 10,000 to the base 10, right? Now, if I do the log here, your answer is going to be 2, right? And here, your answer is going to be 3. Here, your answer is going to be 10, 4. Right? Why? Because this thing can be written as 10 square, and then log of x raised to the exponent n is n log x. So 2, and here log 10 to the base 10, which is 2. Here 3 log to the log of 10 to the base 10, which is here log 10 to the base 10. It is 4. Right? So uh, if you look at the log values of all these three numbers, so can I say here, can I represent this log value as 2 plus 0.0000, right? This one here is 3 plus 0.0000. This thing here is 4 plus 0.0000. Okay, so because I just want to represent this log value as a combination of characteristic and mantissa. So here, if you see here, the characteristic, it is 2. Here the characteristic is 3. Here the characteristic is 4. Okay, so if you have to find the number of digit, what you need to do is you have to do characteristic plus 1. Number of digit, it's going to be ch plus 1. Okay, so here number of digit n would be ch plus 1. Here again, number of digit is going to be ch plus 1. Now come to this one. Here characteristic is 2, so 2 plus 1, 3. Number of digit 3. Here number second, here the characteristic is 3. Okay, so the number of digit is going to be, it's going to be 3 plus 1, 4. 1, 2, 3, 4. Here the characteristic is 3, so number of digit, it's going to be 4 plus 1. 1, 2, 3, 4, 5. 5. 4 plus 1, 5. So always remember that, the number of digits in any given number, it's going to be ch plus 1, characteristic of log plus 1. Okay, characteristic of a log plus 1. Now see here, if you take any number between 100 and 1000, so any number between 100 and 1000, it's going to be a 3-digit number. So you will see that the characteristic of any given number between 100 and 1000, it's going to be 2 plus 0 point so on. Like for example, 999 is going to be 2.0 point something, right? So there is no way that you will get characteristic 3 of any number between 100 and 1000, because the characteristic of 1000 is 3. So any number before 1000 and after 100 is going to have a characteristic of 2. Same here. Here characteristic is 3. So if you take any number, okay, for example, here if I take 1000, if here I take 5000, okay, 5000. So again for 5000, it's going to be 3 plus 0 point something. Okay, 9000, characteristic is going to be 3 plus 0 point something. Okay, so any number after 1000 and before 10,000 is going to be have a characteristic of 3. Okay, so that's why the number of digits in any number from 1000 to 10,000, it is going to be 3 plus 1, 4. I hope it made sense to you. Okay, now come to the example. Come to the example. Come to the example. Come to the example. You have to okay, you have to find the number of digits. Find the number of digits in 6 raised to power 20. Okay, now you have to find number of digits in 6 raised to the exponent 20. Okay, so what I need to do here, uh, I know that if I get characteristic somehow, then what I will do is that I will just do characteristic plus 1. That is going to be the number of digits. So, but to get the characteristic, I have to find the log. So log of 6 to the base 20 and common log. Okay, so it's going to be 20 log of 6 to the base 10. So which is going to be 20. Here, this thing can be written as, it can be written as 2 multiplied by 3, right? 6 can be written as 2 multiplied by 3. And now what I can do is I can use the product rule. 20 multiplied by log of 10, 10, sorry, log of 2 to the base 10 plus log of 3 to the base 10. Okay, right? So here it's going to be it is going to be 20, and here log of 2, it's going to be 0.3010, and log of 3, it's going to be 0.4771, right? So this thing, it's going to be 20, and here 0.3010, 4771, 1877. So 0.7781. So if you multiply by 2, 16, 15, 15. So it's going to be 15562 and 20. So it's going to be 15.562, because here you have 20. So it will cancel 1 0 in the denominator. So it's going to be 15.562. Now, if you break this value into integer and fraction, it's going to be 15 plus 0.562. So the characteristic is 15. So number of digits, it's going to be characteristic plus 1, which is equal to 15 plus 1, that is 16. So number of digits are going to be 16. I hope it makes sense. Okay, now go to the next application. Okay, go to the next application. The next application is common logarithm application, right? So next application is second application again, arithmetic. Okay, in arithmetic it's finding zeros after decimal and before a non-zero, and before any significant number or significant number or non-zero digit. Okay, for example, what does it mean? For example, here this is 0.001. Okay, so finding zeros after decimal and before any significant number is means that finding zero after decimal and before significant number means before any non-zero digit. Okay, so means we have to find this. So how many zeros after decimal and before significant number? Two zeros. Here after decimal and before significant number, three. Understand? So the common logarithm is also used to find out the number of zeros after decimal and before any significant digit. Okay, so here what we can do is let's take the first, we will try to understand. So here I can take few numbers. This is 0, 0, 1, and this is 0, 0, 0, 1. Okay, so if we take the log, so this is going to be if you take the log, it's going to be log of 1 by 100 to the base 10. This is going to be log of or 10 minus 2, and this is log of 10 minus 3 to the base 10, log of 10 minus 4 to the base 10. So this is going to be minus 2. This is going to be minus 3. This is going to be minus 4. Why? Because log of 10 to the base 10, it's 1, right? Log of 10 to the base 10, it's 1. So minus 2, minus 3, minus 4. Now, when we have to find the number of zeros, okay, finding number of zeros. So when we have to find number of zeros, number of zeros, number of zeros, number of zeros. So number of zeros, it's going to be, we have to take the, now again, we can break it down, minus 2 plus 0 0.0000, minus 3 plus 0 0.0000, minus 4 plus 0 0.0000. So the number of zeros, it's going to be the magnitude of characteristic minus 1. See here, the magnitude is 2 minus 1. So how many zeros? After decimal and before significant figure, 1. Here, again, magnitude of characteristic minus 1. So 3 minus 1, 2. How many zeros? 2 zeros. Here, characteristic magnitude minus 1. So 4 minus 1, 3. So how many zeros? How many zeros between, sorry, after decimal and before significant figure? It is 3. Okay, so that's how you have to do it. Okay, now we can take one example which can bring more clarity. So we have to find find the number of zeros in 2 raised to the exponent, in 2 raised to the exponent minus 50, right? Yes. Okay, so you have to find that. Now see here, 2 raised to power minus 50, it is equal to 1 by 2 raised to power 50. So you can see like there are going to be lots of zeros after decimal and before the first significant figure, right? Because this thing is going to be a huge quantity. Okay, so how to do it? We'll take the log, right? So if you take log of 50, sorry, 2 raised to power minus 50 to the base 10, it's going to be minus 50 multiply by log of 2 to the base 10 y. Here log of x raised to power n, that is n log x. So this thing is going to be minus 50, and log of 2 to the base 10, it is 0.3010, right? So here, if I multiply, okay, so this thing it's going to be um, 0.3010 multiply by 50. So this thing it's going to be this thing here 1 2 3 4 and 0 5 1 5 0 15. So 15050, right? 15050, and the decimal it's going to be here. Okay, so you can see here that the characteristic it is minus 15, and here the Mantissa, now this value is minus 15 and the Mantissa is 0.050. Now, Mantissa cannot be negative, right? This thing cannot be negative. It has to be positive. So what I will do here, I will minus plus, right? 50, right? So it's going to be minus 16 plus, and this is going to be 0 point, right? Uh, this thing is going to be 0, then 10 minus 5 5, and then 9 minus 10 minus 5, and here 9 9, right? 0, right? 110, yes. So the characteristic is minus 16, right? But we have to take the magnitude. So the number of digits, it's going to be characteristic minus 1. So it's going to be 16 minus 1, 15, right? I hope it is clear to you. Okay, so that's how you can find the number of zeros, and you can also calculate the number of digits. Okay, so these are the two use cases of common logarithm in arithmetic. Okay, so that's how I'm just concluding the session here. So next time we are going to have talks on a few other things, inequalities, and we are also going to look at how to sketch the graphs for logarithmic function. So that's all for today. Have a great time. Bye bye. See you